Hello all, welcome to my YouTube channel. In this session, I will talk about how you can fine tune a foundation LLM model using the concepts like LoRA and quantization. So this would be a two-part series. So in the first video, in this video, I will talk about the very core concepts of LoRA and quantization. And in the next video, which will be releasing tomorrow, the part 2 there I will show you the code implementation of doing the instruction fine tuning using quantization and LoRa on top of a Llama 2 model. Now let's get started. So these are the topics which will be covered in this session. So first we will start with what is the need for fine tuning a foundation model. Then we will look through how the general fine tuning process works in case of a normal LLM, right? Then we will talk about how what are the problem associated with fine tuning, and slowly we will try to build the concept of LoRa and quantization, and then we will see the benefits of LoRa. How what are the benefits if you want to fine tune your foundation LLM model using the concept of LoRa, right? And part 2, which will be released tomorrow, there we will talk about the code implementation using the concepts which we will learn in this video. So yeah, let's get started. So we can use a foundation LLM model, and there we can start writing a prompt, right? And we can like a prompt can be asking the LLM to do a text summarization task or a sentiment classification. Any prompt we can write, and we can pass that prompt along with the data to the LLM, and LLM will give us back the desired output, right? It may happen that the desired output is not that optimal. And in that case, what we need to do is we will do in context prompt fine tuning, right? So what we will do is we will pass more context in the prompt. In case of like prompt engineering, what we generally do is we give certain examples, right? We can give one shot or two short examples on the task, based on the task which we are performing, and which will kind of give the LLM the context, and based on that LLM can perform well, right? So that's what the in context prompt fine tuning is. So generally we do this two things, the prompt engineering and in context prompt fine tuning, when we only have the API access of my LLM. We do not have the full access of my LLM. We only have API access. So we like pass our prompt to as a API call to my LLM, and LLM gives back that result, right? So after all this also, the results are not desired, right? And the result has not improved by doing a prompt engineering or by doing a in context prompt fine tuning. The results which we are getting, those are not optimal which we desired at the starting, right? So in that case you might think that the LLM is not generalized to the data on which you are trying to do a modeling or trying to do a classification or text summarization or any NLP task, right? And this foundation LLM models are generally pre-trained or fine-tuned on the large internet text, right? So they are not very much specific to a domain, right? So for an example, if you are working with a biomedical text, it might happen that using a foundation LLM, you might not get the optimal results, right? So in that case, you want to go for a fine tuning, right? So by doing the fine tuning, what you want to do is you want to generalize the foundation LLM to your own data, right? And where using your own data, you will do prompt engineering and you will get the optimal results, right? So basically, the fine tuning we can divide in two parts. One is like full fine tuning, where we will update all the parameters of my foundation LLM, and then there is parameter efficient fine tuning, right? Where we will kind of use some concept of adapters, where we can add certain adapter layers on top of my pre-trained weights and only train those adapters. Or you can use the concept of LoRa, where we will train certain low rank representation of my weight matrices associated with attention mechanism, right? So in attention mechanism, we have generally three matrices, right? Query, key, and value. So it might have it you might what you can do is you want to create a low rank representation of those either of this any matrices, and only fine tune those weight matrices. You do not touch the frozen weights of my pre-trained model, right? So yeah, don't worry about it. We will talk in detail what this parameter efficient fine tuning in this video. So let's first talk about the full fine tuning, right? So in case of full fine tuning, we have our input data, and we have, if you have a neural network, so this all this LLMs are basically a neural network, right? With attention mechanism, they have hidden layers, and in the hidden layers, they are associated weights like W1 and W2. So we kind of pass our input data to across the hidden layers, and then we get the output. And once we get the output, we try to compare this output to the actual target, and when we calculate the loss, and once we have the loss, we do weight updates, like we kind of optimize the weights which are associated with hidden layers, and also in some of the cases output layer also that can have associated weights also, right? So we kind of do the weight optimization of this layers, and we kind of try to match our output to the actual target value, right? uh, yeah, so let's look into the steps in detail, right? So first, if you want to do a full fine tuning, what we need to do, we need to have a large amount of data set, right, which we need to load in the memory, because we are doing a full fine tuning. So in that case, we will need a huge volume of data to train the foundation LLM model, right? So it's not that you have 1,000 examples and you want to do a full fine tuning, right? So that will not give you optimal results. So you need to have a huge database or huge training data set on top of which you will do the full fine tuning. Then you also need to load this pre-trained weights associated to the foundation LLM in your memory. Then you will do a forward pass through the network, and you will calculate the loss, and you will do a gradient descent or a weight optimization, which are associated to the pre-trained weights of my foundation LLM model, right? And then after this, we will kind of get the optimized weights, which we will use for the downstream task, right? But all this has certain challenges, right? So let's talk about the challenges. So as I mentioned, like we need to have a huge amount of data set, and also we need to load the model weights, which are very huge in number in case of LLMs, right? So in case of like chat GPT, there are more than 175 billion parameters which are there, right? So all this you need to load into your memory to do this steps, right? So that requires a large amount of memory, right? And which will be also associated with training time. So training time will be also large, because we are touching huge volume of weight updates, and we are doing huge volume of weight updates, which will have associated training time, and also you need to have associated cost related to that, right? So that cost can be in terms of gathering GPUs, buying GPUs, putting human resources into action. So all this has a huge amount of time and cost associated with this, right? And it might also happen that once you do the fine tuning, full fine tuning, your results are not optimal, right? Because your data set was low, and you have not implemented proper techniques to do the weight optimization. So it might happen that your all the experiments went in vain, and your results are not optimal, right? And also there is a huge risk of catastrophic forgetting. So what this catastrophic forgetting is, so the LLMs are generally trained for next word prediction or text generation, right? So ChatGPT is like a decoder part of transformer network, and which generally does the next token prediction or next word prediction, right? So if you train your a pre-trained model using your data set, it might happen that it will forget the task for which it was pre-trained, right? So, and generally it does well on the certain task, right? It might happen that it might forget those behaviors, those patterns, and it will not be able to do the task for which it was previously pre-trained, right? So that's what we call as catastrophic forgetting. So that can also happen, right? Okay, so now just to give you a recap, like we have our pre-trained weights that we kind of optimize during this full fine tuning. And once we do the weight optimization, we kind of get the updated embeddings, right? Which is like, which will be, we will get after doing the weight optimization of my pre-trained weights, right? So this is how it, you can visualize the full fine tuning process. Now let's talk about LoRa, right? So LoRa is nothing but low rank adaptation. So before going to low rank adaptation, let's talk about two critical concepts which you should be aware of, right? First is like matrix decomposition. Okay, so I will try to explain this in very simple way. So if you know your the elementary math, right? So we can decompose 50 by using these two products, right? 5 multiplied by 10 will give you 50, right? So similarly, we can decompose a weight matrix like this weight matrix, which are associated to a pre-trained foundation LLM model, which is like W. That also you can decompose to two matrices, right? A and B. So once you do the dot product of this A and B, you will get back the same shape of my pre-trained weights, right? So the dot product of A and B will give you back the shape which was originally there for the pre-trained weights, which is like DW, right? So this is what the concept of matrix decomposition is. Then the another concept which you need to be mindful of is the rank of a matrix, right? So say, for example, right, we have this matrix, right, where we have three columns. So like C1, C2, and C3. So if you look closely, your C3 column, right? So this column is nothing but the sum of previous two columns, right? C1 and C2, right? So 1 plus 2 equals to 3. So if you just do a plus here for every element wise plus, you will get back the third column, right? So it's C3 is kind of a redundant column, right? You don't need to have that in your metrics, right? So if you have a weight matrix where there are redundant rows, right, which are not linearly independent, right? So those are kind of redundant information we can have in case of a matrix. So just coming back to the definition here, C3 is a linear combination of my C1 and C2. So C3 is not linearly independent column, right? So the rank of a matrix is number of independent column or rows for a given matrix, right? So here the rank of matrix is 2, right? So in case of, for this example, this was like a 4 cross 3 matrix, right? But the rank of matrix is 2. So this T2 is quite less to 4 cross 3, right? Or the dimension of each of my rows and columns, right? So with this understanding, right, if like matrix decomposition and rank of a matrix, let's see what LoRa does, right? So as I talked about, right, what is we can decompose a weight matrix to a two different matrices, right? So in this two different matrices, we can incorporate the concept of rank, right? So it has been shown in that Microsoft paper which they released for LoRa. They mentioned that there exists a low dimensional representation of the pre-trained weight matrix, which is very lower in dimension, right? So so the redundant information you can throw away and you can use the concept of rank, and this rank can be very much smaller than your dimension of original matrices, right? So R is kind of very much smaller if you compare with the A and B. A and B are the shape of my matrices, right? Or the number of rows and columns, right? So if you can decompose this matrix into low rank matrices, then your then once you do the dot product between this WA and WB, you can get back to the original matrix, right? Which is like DW, right? So this is how you can use the concept of rank, and you can throw away the redundant information and you can get a much smaller matrix representation of the original weight matrix, right? Now let's take an example and understand how this can help us, right? And in the end, as I mentioned, like if you do a dot product of this WN and WB, so that can give you the same shape of my original pre-trained weight. So you can add back this original matrix to the low rank representation matrix decomposition, and you can get back the original embedding space, right? Now, for an example here, right? So if I take an example that my original pre-trained weight matrix has a dimension of 2000 cross 5000, right? And if you calculate the number of weights associated to this matrix, that would be very large, right? So that will be like 10 million, right? Now, if you do a low rank representation of my this matrix in a different way, right? So my low rank matrices are like WA and WB, where the rank I am using here is 5, right? Now, this how we choose this 5, that is kind of hyperparameter to the model, but I will show you certain results which are from LoRa paper, which will give you some ridiculous results. Like you can go ahead with very small numbers of this rank and still you can get a very good performance, right? So for an example, like here, the dimensions for WA is like 2000 into 5, and which will give you 10,000. And for similarly for WB, it's 25,000, right? And then if you do the sum between these two, you will get the total number of model parameters as 35K, right? Or 35,000, which is much smaller to the 10 million, right? Which is like at least close to 30% less number of parameters which you need to maintain if you want to just look at this W and WB, which are like low rank representation, right? So this R is nothing but rank of my matrix, right? Rank of my original matrix. And with this representation, you can throw away some redundant rows or columns, and you can have a lower dimensional representation of my original weight matrix. Now, what will happen in case of LoRa, right? Let's try to understand with this example. So as I'm previously, I was giving this example only. We have my input data and we have my pre-trained weight, which are associated, which are coming from LLM. So this is coming from LLM, my foundation LLM model. And these are the low dimensional representation of my this matrix, right? Pre-trained weight matrices, low rank representations in terms of A and B, which has a dimension of A cross R and R cross B. So if I just do a dot product, so the inner dimension matches here, like R and R inner dimensions are matching. So we will get the final output, which will be like A cross B, right? Here also the final dimension is A cross B. So as the dimensions are matching, we can add back this, right? So we pass the input data through my LLM, foundation LLM model, and also using this LoRa representation, right? And in the end, we will add back this two and we will get the output, right? So once we have the output, we can compare this with the target variable and we can calculate the loss. Using this loss, we will not touch this pre-trained weight matrices, right? We will not touch W, but we will only touch WA and WB, right? So we will do the weight updates only in this path of my WN and WB. And with that, we will kind of fine tune our model with very less number of parameters. As I mentioned previously, the example, right, which can be like as close as to 30% of my original weight matrices size, right, or the model parameters which we have. Okay, and in the during the inference time, as the dimensions of my original W and my LoRa low rank adaptions are matching, so we can like combine these two outputs and we can get the final embedding of my input data, right? So this is the concept of LoRa, which I wanted to talk in this video. And okay, let's see what are the benefits we will have if you do this process, right? So one of the benefits is that you can have you can create these low rank adaptation matrices for specific task, right? So for an example, like if you have a task called text summarization and another task is sentiment classification with your domain specific data, right? Now, if you want to do a full fine tuning, you can understand the huge volume of weight parameters that you need to do for this each of these two tasks, right? But what you can do with the help of LoRa is you can create two separate LoRa adapters or two separate low rank dimensional representation using this WA and WB, and you can create task specific adapters or the low rank representations, and during inference times, you will only add back the task-specific LoRa representations to the frozen pre-trained weights, right? So it gives you immense benefit in terms of maintainability, right? In maintainability in terms of weights, in terms of maintaining those weights. So this is one of the benefit which is very specific to LoRa that you can do. So you don't need to bother about uh, updating the frozen pre-trained weights, right? You will only update the low rank representations, which you can also do it for task specific operations, right? Okay, now this are the two things which are coming from LoRa paper. So as I mentioned, like you have a low rank dimensions representation of your original weight matrix, right? So it can come up with a some performance degradation, but in case of LoRa paper, they have mentioned that if they do this operations on GPT-3, the performance are quite similar to the if you do fine tuning, full fine tuning or any other process, right? And this thing, like how we will choose the value of R, right? So you can see that using ridiculous value of R equals to 1, right? With that also, if you fine tune this query key and value matrices, and you will get very good performance by just using R equals to 1, right? And using R equals to 64, you will see there is not a huge jump in the performance, right? So with this dimension like R equals to 1 or R equals to 2, you can get state of the art performance if you use the concept of LoRa, right? Okay, with this, I hope you get an understanding of LoRa, how this works. Now let's talk about the another concept. Okay, so before that, let's see what are the benefits in terms of everything which we talked about, right? Less parameters to train and store and maintain, which I've already talked about, which will in turn give you the less memory requirements, right? And which will also in turn give you the faster training time. So you can do the experiments in quick manner and get the result. And your training time will be much more lesser if you use the concept of LoRa, right? And also the benefit of using task specific LoRa adapters, which you can switch between while doing different tasks which are related to NLP, right? And also it gives you the immense benefit of no risk of catastrophic forgetting, right? So as we are not touching the pre-trained weights, those are kind of frozen, so there is no chance of catastrophic forgetting, right? Yeah, so the another concept we wanted to talk was like quantization. So along with very small memory requirements which are related to LoRa, you can also reduce the memory requirements by using a low precision representation of your weights, right? So if in general we have weights which are like the data type of that is float 32, right? So this is kind of tells you what is the precision of my data type, and this is kind of range of the value, and this S is nothing but a sign bit, whether it is like 1 or 0 based on the positive and negative value. So it will take larger memory space if you go ahead with FP32, right? Now, if you go ahead with half precision, your memory requirements will be much more lesser, right? So here we are kind of reducing the lesser number of range of numbers that we can represent using FP16, and also we are kind of reducing the precision range, right? And with that, like if you do a quantization, what it generally does is if the weight is like something like this, right? 3452.3194, right? And if you do a 8-bit integer representation, so all this integer representation will be removed, and sorry, floating representations will be removed, and you will get an integer representation of my number, right? Which is like you will go from this to this, right? Where we are starting with 32-bit representation, we will go ahead with 8-bit representation, right? Yeah, it will kind of give you some degradation in the model output performance, but will give you the benefit of quickly loading the model weights, working with commodity hardwares like one GPU machine. And there you can do the fine tuning operations, right? Using this concept of quantization. Right now, let's take an example of how this quantization works with a simple 8-bit 0-point quantization process, right? So if my weight matrix looks like this, right, which is kind of a 3 by 3 matrix with random values initialized for weight, or you can say like these are the optimal values of my weight parameters, then we can like do a quantization process on top of it, and we can have a lower precision representation, which will be like this. The values will be like this. Now let's see how these values are calculated, right? So the example which I am talking here is let's create weight matrices with the shape of 3 cross 3, and this is the value. This is similar to the value which I have been using here, right? So then what the steps are like for this 8-bit zero quantization is, at first we will calculate the max value along with this whole array, which is like this value is the max value, which will be coming up here, right? Then using that max value, we will calculate a scaling factor. So this scaling factor is we are dividing 127 by the max value. Now, why this 127 is because using 8-bit quantization, we will represent the values in the range of -27 to +127, right? So once we calculate the scaling factor, we will multiply the scaling factor with the each elements of my array, and they will then we will kind of round off those values, right? So and it will be kind of a 8-bit representation, right? 8-bit integer representation. So this is how you can go ahead, go from 32-bit floating point representation to a 8-bit integer representation, which will save a lot of space for you in terms of loading the model weights and the parameters, right? Yeah, so that's all about quantization. And yeah, so I will talk about this code implementation of LoRa in the part 2 of this video. And there we will see how we can implement the concept of LoRa using the foundation LLM model like Llama 2, right? I hope you like this video. Please subscribe to this channel for more such content. Thanks for your time. Let's see you in the part 2 of this video.